Greetings, viewers. Join us for this video session delving into the network communication aspects associated with wireless sensor nodes. This is part of our IoT lecture series presented by iNet Tech Talk. In this video session, our goal is to explore the following topics: wireless sensor nodes, architecture and basics of wireless sensor networks (WSN), comparisons between WSN and ad hoc networks, highlighting similarities and differences, challenges encountered in WSN, routing protocols employed in WSN. Now, let's examine the components and features linked to a smart sensor node. It consists of a sensor unit tasked with collecting information related to specific types or physical parameters, such as temperature, humidity, moisture, gases, altitude, speed, acceleration, location, or light. A processing subsystem is integral, encompassing an analog-to-digital converter that transforms analog signals received from the sensor unit into digital format. This enables the computing unit to process the incoming data effectively. Following this, there is a microcontroller and local memory dedicated to data processing. The processing unit might incorporate onboard memory or be connected to a small storage unit. This component oversees the operations, facilitating the sensor node to execute sensing tasks, run relevant algorithms, and engage in wireless communication with other nodes. Now, let's delve into the transceiver feature of the sensor node. This involves a radio subsystem or transceiver designed for wireless data communication. The communication between any two sensor nodes is facilitated by these transceiver units. A transceiver unit is responsible for executing essential procedures to convert the bits intended for transmission into radio frequency (RF) waves and to recover them at the receiving end. Essentially, this unit serves as the connection point between the wireless sensor network (WSN) and the broader network. The power unit typically comprises a battery, although alternative energy sources are also viable. Every component within the wireless sensor node draws power from this unit. The limited capacity of the power unit necessitates energy-efficient operation for each component's tasks. Now, let's explore the architecture associated with wireless sensor nodes. A wireless sensor network, WSN, comprises numerous small, low-power, and cost-effective sensor nodes deployed randomly or manually across an unattended target area. These sensor nodes collect local information at regular intervals, process the data, and transmit it to a remote base station (BS) or sink through either single-hop or multi-hop communication. The communication of sensed data to the sink varies based on the diverse applications of the sensor network, encompassing continuous, event-driven, query-driven, or hybrid approaches. The architecture of a wireless sensor network, WSN, is characterized by two main structures, flat and hierarchical. In a flat sensor network, each sensor node shares an equal responsibility for efficiently performing sensing tasks. The sensed data is then transmitted to the sink using either single-hop or multi-hop communication. In a single-hop type communication, the data from the sensor node is directed to the base station for further communication, whereas in case of multi-hop communication, a sensor node sends the data to another node, and then depending upon the communication strategy, the data is then directed to the base station for further communication. Single-hop communication is suitable for small area sensor networks, particularly when the sink is located in close proximity to the region. In contrast, multipath communication is employed in large area networks. In this scenario, each sensor node chooses another sensor node as the next hop relay node to efficiently forward the data to the sink. In a hierarchical network, sensor nodes are organized into distinct groups referred to as clusters. Each cluster is headed by a leader known as a cluster head (CH). Within this structure, all sensor nodes are responsible for sensing local data and subsequently transmitting it to their respective cluster head. The cluster heads, CHS, play a crucial role by aggregating the local data within their clusters. Subsequently, they transmit the aggregated data to the base station, BS, either directly or through other cluster heads. The operational dynamics of a cluster-based wireless sensor network, WSN, incorporating both single-hop and multi-hop communication between cluster heads and the base station, are illustrated in the accompanying figure. Let's now delve into the section of this video that examines the similarities and differences between wireless sensor networks and ad hoc networks. Both wireless sensor network, WSN, and ad hoc networks share common characteristics. Distributed wireless network. Both WSN and ad hoc networks operate as distributed wireless networks, where nodes communicate with each other without the need for a fixed infrastructure. Multi-hop routing. Routing between two nodes in both types of networks may involve the use of intermediate relay nodes, requiring multi-hop routing to establish communication paths. Limited battery power. Nodes in both WSN and ad hoc networks are typically powered by small batteries, highlighting the importance of energy efficiency. Energy conservation. A key objective for both types of networks is minimizing the energy consumption of the node's batteries. This goal is essential to extend the overall network life and maintain connectivity over time. Let's now explore the distinctions between wireless sensor networks, WSNs, and ad hoc networks. Let us now focus on the application part related to both types of networks under consideration. WSNs are specifically designed for applications that involve sensing and collecting data from the environment, such as monitoring physical conditions. Sensor nodes are not designed for human operation, instead, their interaction is with the environment. Ad hoc networks, on the other hand, are more generalized and can be applied to various scenarios, including data sharing, communication, and collaboration. Ad hoc networks or mobile ad hoc networks, MANET, are typically in proximity to humans and devices such as mobile phones, laptops, personal digital assistants, PDA, etc. The quantity of nodes within a wireless sensor network can range from several hundred to potentially extend into the thousands. Sensor nodes in WSN are frequently characterized by resource constraints and specialization for sensing tasks. These nodes are susceptible to failure and energy limitations, given their operation on small batteries. In contrast, in the case of ad hoc networks, nodes may possess more diverse capabilities and can be tailored for general-purpose devices. Ad hoc networks typically have fewer devices designed for direct human operation. These networks are equipped with superior energy-efficient battery and power management systems, ensuring a longer lifespan and extended working hours. Replacing sensor nodes when their energy is completely depleted is an extremely challenging task. The unique addressing of sensor nodes is not always feasible in sensor networks, and even distinguishing between neighbors becomes problematic. In contrast, in ad hoc networks, it is relatively straightforward to recharge nodes with electricity. Node identifications in ad hoc networks involve globally unique IDs, example, MAC address or IP address, making routing problems address-centric. Let's discuss resources. In wireless sensor networks, WSN, the computing capability of sensor nodes is highly limited, memory is constrained, and the transmitting equipment operates with low power consumption. On the other hand, in ad hoc networks like mobile ad hoc networks, MANETs, typical components such as processors often boast capacities in the hundreds of megahertz range, memories are measured in dozens of megabytes, and rechargeable batteries can sustain operation for several hours. The use of flash memory provides ample storage space, enabling the local storage of complex statistics. In the communication paradigm of wireless sensor networks, WSN, direct sensor-to-sensor communications may be infrequent. However, multicast and broadcast transmissions are so prevalent that their effects must be carefully considered. In certain scenarios, the failure of individual nodes may not be significant unless it involves the sync, which presents a problem. On the other hand, in mobile ad hoc networks, MANETs, nodes are considered peers, meaning no node is inherently prioritized over another. Transmission could occur between any pair of nodes, highlighting the decentralized and egalitarian nature of communication in MANETs. Data aggregation holds paramount importance in sensor networks, whereas it is deemed not important in the context of ad hoc mobile networks. In sensor networks, sensor nodes engage in aggregating local data before transmitting it to the next node, a practice that is not done in ad hoc mobile networks. This data aggregation strategy in sensor networks aims to achieve maximum bandwidth utilization and reduce energy consumption, while in ad hoc mobile networks, such practices are considered to have a moderate level of use. Wireless sensor networks, WSNs, encounter a variety of challenges and issues that influence their functionality and practical implementation. Some key issues included are discussed in the next section of this video session. Now, let's understand the challenges due to the limitations posed by restricted energy resources. Sensor nodes are commonly equipped with small batteries, making energy consumption a pivotal concern. Extending the network's lifespan while ensuring consistent and reliable operation presents a significant challenge. Employing energy-conserving communication and computation methods becomes imperative. In a multi-hop wireless sensor network, WSN, each node assumes a dual role as both a data sender and a data router, leading to increased power requirements. The failure of certain sensor nodes due to power depletion can result in noteworthy topological changes, necessitating packet rerouting and network reorganization. Wireless sensor networks, WSNs, frequently function in dynamic and unpredictable environments, presenting challenges in sustaining reliable communication. Factors such as signal interference, obstacles, and fluctuating signal strength can impact the stability of communication links. Strategically placing sensor nodes in designated locations is vital for achieving effective coverage. In mobile wireless sensor networks, where nodes may be relocated or deployed on mobile entities, preserving connectivity and ensuring optimal coverage poses a challenge. The deployment of nodes in WSN is contingent upon the application and influences the routing protocol's performance. This deployment can be either deterministic or randomized. In deterministic deployment, sensors are manually positioned and data follows predetermined paths. Conversely, in random node deployment, sensor nodes are dispersed randomly, forming an ad hoc infrastructure. Ensuring effective data aggregation and processing is crucial for minimizing data transmission and conserving energy. Developing algorithms and protocols that enable intelligent data processing and aggregation presents a challenge. Given that sensor nodes may produce considerable redundant data, aggregating similar packets from multiple nodes becomes a strategy to reduce the overall number of transmissions. Data aggregation involves merging information from various sources based on a specific aggregation function. Converge casting refers to collecting information upwards from the spanning tree following a broadcast. Now, let's explore the data delivery model, specifically examining the time-driven and event-driven data models. The time-driven model is likely to do something for applications demanding periodic data monitoring. In this model, information from sensor nodes is consistently gathered and monitored at regular intervals. Contrastingly, the event-driven model involves an immediate reaction to sudden and significant changes. In this scenario, sensor nodes provide information when they observe a drastic change during monitoring. In the query-driven model, sensor nodes receive query signals, responding by providing data corresponding to the specified situation to either the base station or another node in the network. Within the hybrid model, any combination of the aforementioned techniques adapted to the specific monitoring environment constitutes a hybrid utilization of sensor nodes. In case of node-linked heterogeneity, based on the application, a sensor node may assume varying roles or possess different capabilities. The presence of a diverse set of sensors introduces numerous technical challenges related to data routing. Additionally, data reading and reporting from these sensors can occur at different rates, adhering to various quality of service (QoS) constraints and adopting multiple data reporting models. Certain sensor nodes may experience failure or obstruction due to reasons such as insufficient power, physical damage, or environmental interferences. In such instances, fault-tolerant networks become imperative. It may be necessary to proactively modify transmission powers and signaling rates on existing links to minimize energy consumption. Alternatively, rerouting packets through network regions with higher energy availability while excluding inactive nodes may also be considered. Scalability encompasses the deployment of a substantial number of sensor nodes within the sensing area, ranging from hundreds to thousands or even more. Any routing scheme employed must effectively operate with this considerable number of sensor nodes and be prepared to accommodate additional sensors as the need arises. Furthermore, routing protocols designed for sensor networks should possess scalability to efficiently respond to environmental events. Routing messages to or from mobile nodes poses increased challenges due to the significance of route and topology stability. This complexity is particularly pronounced in scenarios involving mobile phenomena, such as target detection or tracking applications. Effective implementation of a routing protocol is essential to ensure the smooth transmission of data from sensor nodes to the base station, BS. Typically, the bandwidth demands for sensor data are relatively low, ranging from 1 to 100 kilobits per second. The design of media access control protocols, MAC, is closely tied to the transmission media. These MAC protocols encompass various multiple access approaches, including random, controlled, and channelized methods. The elevated node density in sensor networks prevents them from achieving complete isolation from one another. Nevertheless, this condition does not necessarily impede the variability of the network topology or the potential reduction in network size caused by sensor node failures. Connectivity is contingent on the potentially random distribution of nodes within the wireless sensor network, WSN. In these networks, each sensor node perceives a specific view of the environment. The view of the environment for a particular sensor is constrained both in terms of range and accuracy, allowing it to cover only a limited physical area. In numerous applications, the preservation of energy is crucial as it directly impacts the network lifetime. As energy levels diminish, there might be a need for the network to compromise the quality of results to mitigate energy dissipation in the nodes, thereby extending the overall network lifetime. Now, let's explore the various routing algorithms associated with wireless sensor nodes. These algorithms are categorized into three groups: flat, hierarchical, and location-based. In the flat architecture, the routing algorithms include flooding and gossiping, spin, sensor protocols for information via negotiation, and directed diffusion, DD. Within the hierarchical architecture, the routing algorithms consist of leech, low-energy adaptive clustering hierarchy, Pegasus, power-efficient gathering in sensor information systems, and two-tier data dissemination, TTDD. For the location-based architecture, the routing algorithms encompass geographical and energy-aware routing, gear, and greedy perimeter stateless routing, GPSR. In our discussion, we will only look into the flooding routing protocol associated with wireless sensor network. In the flooding protocol, each sensor that receives a data broadcast forwards it to all of its neighboring nodes, and this process continues until the packet reaches the destination or the maximum number of hops for the packet is reached. Upon reaching the destination, the least or shortest path is chosen, as indicated by the arrow. While flooding is a straightforward approach, it can lead to issues such as excessive energy consumption and redundant message transmissions, making it less efficient for large-scale sensor networks. To address these challenges, more advanced routing protocols, such as those incorporating data aggregation or hierarchical structures, are often employed in practical WSN deployments. There are generally two types of flooding protocols: uncontrolled and controlled flooding. In uncontrolled flooding, each node unconditionally broadcasts packets to all of its neighbors. Without conditional logic to prevent the indefinite recirculation of the same packet, there is a risk of broadcast stalls. Controlled flooding employs two algorithms to enhance reliability: SNCF, sequence number controlled flooding, and RPF, reverse path forwarding. In SNCF, the node appends its own address and sequence number to the packet. Since each node maintains memory of addresses and sequence numbers, it immediately drops a packet if it has been received before. On the other hand, in RPF, the node only forwards the packet if it has been received from the next node. If the packet is received from any other source, it is sent back to the original sender. There exist various variants of flooding algorithms. Bidirectional flooding, in this variant, each node serves as both a transmitter and a receiver. Unidirectional flooding, each node attempts to forward every message to all its neighbors, excluding the source node. This ensures that every message is eventually delivered to all reachable parts of the network. While flooding algorithms can be simple, in some cases, complexity is necessary to avoid issues like wasted duplicate deliveries, infinite loops, and to enable messages to expire from the system. A variation known as selective flooding addresses these concerns by sending packets only to routers in the same direction, reducing unnecessary transmissions. Selective flooding has the advantage of using every path through the network, including the shortest path, making it straightforward to implement. However, flooding can incur costs in terms of wasted bandwidth. In scenarios like ping floods or denial of service attacks, it may harm the reliability of a computer network. To mitigate potential issues in flooding, precautions can be taken, such as implementing a hop count or time to live (TTL) count with each packet, considering the number of nodes the packet may traverse. Having each node track every packet seen and forwarding each packet only once. Enforcing a network topology without loops to prevent endless circulation of duplicate packets. In summary, we have covered several key topics in this video session. We began by exploring the smart sensor node and its components, delving into the architecture of wireless sensor nodes. We compared the similarities and dissimilarities between wireless sensor networks, WSN, and ad hoc networks, addressing the challenges and issues specific to WSN. Our discussion also extended to the various routing algorithms employed in WSN, and we concluded by examining the advantages and disadvantages associated with these routing algorithms. This comprehensive overview provides insights into the essential aspects of wireless sensor networks and their applications. As we wrap up this insightful video session, we hope you found the exploration of wireless sensor networks both informative and engaging. If you are eager to delve deeper into the realms of education, technology, and travel, we encourage you to subscribe to our YouTube channel, iNet Tech Talk. By subscribing, you'll stay updated on our latest content, ensuring a continuous journey of learning and discovery. Thank you for joining us, and we look forward to sharing more valuable insights with you in the future. Subscribe now for a vibrant blend of education, technical knowledge, and exciting travel experiences.